Good morning, dear friends, and we will do lecture about the functions, right? And can you see the share page? And so what was our last part? Yeah, we will talk about as soon as I can do, I will evaluate your midterm paper, then I will announce from the UBIS. And now we were talking about as a last part uh, function properties like or classification one-to-one onto an invertible function, and there is also graph forms function. And let's write the example. If we have like the f1 function, f1 of x is equal x squared, and then f2 x is equal to the power x, and f3 x is equal x to the power 3 minus 2 times x to the power 2 minus 5 times x plus 6, and f4 x is equal x to the power 3. We have 4 different function. Okay, let's draw that function graphical form. Here is the x line, and this is the y. X line is the domain, right? Y is the codomain, right? Did we do any explanation for that before? Yeah, I think so. Yeah, this is the x is the domain and y is the range. Okay, range is also target or range set. Here is the y as a codomain, and if you want to draw x squared, okay, like that may be better for the taking video vision. And here is the x squared graph, and y and x. This is the graph of f1. Okay, I'm trying to do some place, and then I will draw f2x. Okay, here again x and y line. So this is gonna be like that. This is the y as a target, and x. This is the f1x graph, and this is the f2 x is equal to the power x. and F3. So F3, I hope I'm gonna do all in that place. I mean the graph. So this is F3. It is like that form, and this is the Y and X, and last one. Okay, this is easier, I think, than F3. This is the F4, again Y line and X. You know, Y is the codomain and X line is the domain. And here is F3 and F4. F3, X, and F4. Oh, I'm sorry, F4X. Not F04, F4X. So we were talking about before the midterm, you know, there is the one-to-one, and there is also, you know, some classification like what a one-to-one, onto, and invertible properties, right? So if we look at, you know, F1, you see if you put here as a 1 minus 1, okay, as an example, and here is minus 1, and here is the 1. Both are going to come to point as about 1, right? If you put minus 2, it is going to like 4. Okay, minus 2, and 2 is here, and both is going to be like 4, 1, and 4. So do you think that this is one-to-one function, F1? No, this is not one-to-one because from the domain set, we have minus 2 and 2 and minus 1 and 1 coming to do, you know, same image set. So this is not one-to-one. How about onto? This is, do you think that this is the onto function? So we will say not one-to-one. You make it table. It is the easy to write everything in together. F2, F3, X, and F4. And there is the, you know, one-to-one and onto and invertible. You know, writing is taking some more time. That's why I'm writing like that. In table, invertible, and F1 is not one-to-one, right? not onto, because not covering the minus side of the y, not covering the minus side, and it means this is not also invertible, right? So how about f2x? f2x 1 to 1, yeah, right, Zainab, this is 1 to 1 because when you write some value, it's come to y as a one value and one value for each of, domain member will come to only one codomain member. There is only one image for each element of domain set. So this is 1 to 1. How about onto? Not onto, right? Why not onto? Yes, exactly. If we get that two properties, then we will say this is the invertible, and we can say this is the invertible. And how about f3? Is it 1 to 1? Not 1 to 1. Why? Because when you take, for example, one value, for example, what? There is gonna be two codomain value. That's why this is not 1 to 1. And how about onto? It is covering the minus side and plus side of y as a target domain. So we can say this is the onto. And how about invertible? No, because we have to get that two properties. At that time we will say this is the invertible. And f4, you see, for each of x value we have only one y value. So this is the 1 to 1, 1 to 1. And there is, okay, I have some problem. I'm going to reduce to streaming. Okay, I hope this is the faster. And f4, we said this is the 1 to 1, right, dear friend? 1 to 1. And this is also onto because for y minus side, for plus side of the y line, there is the some x value. This is also onto. So if we have that two condition, then we will say this is the invertible. Okay, next one. This was the some function classification of properties. Then different type of function as a permutations. Permutations. Okay, there is the definition, and invertible we know the invertibles as a bijective. There is the second, explanation for the invertible function. There is the sigma as a that function from x to x is called permutation on x. So at that condition, we will say this is the, permutation function. And there is, invertible means there is the one-to-one and on-to also working in that function. The composition and inverses of permutations on x, it means the sigma function, the identity function on x are also permutations on x. So let's say, as an example, or we have as a x set 1 to n, then permutation sigma on x can be denoted by like that. One to J1 and 2 J2 and 3 goes to J3 and so on. This is the NJN. So here is the, our domain set. Let's change the pen. Okay, this is the domain. And here is the, you can say target or codomain. And what else? So this is the our permutation function. And we can write the example again. So this is the formulated example, and let's write some numerical example. Like there's the sigma again, and we have, okay, let's define the x set also. X is equal 1 to 6. 1, 2, 3, 4, 5, and 6. And there is the sigma as a permutation function. We have, domain 1, 2, 3, 4, 5, and 6. And 1 goes to 4. And 2 goes to 6, 3, 2, 2, 4 to 5, and 5 to 1, and 6 to 3. And let's write one more like the tau. Again, we have domains at 1, 2, 3, 4, and 5, and 6. And 1 goes to 6, and 4, and 3, and 1, 2, and 5. This is our, permutation function. If we want to, for example, test, for example, sigma 2 is equal 6, right? And here is the tau of 2 goes to 4, like that. Okay, this is the page 1. And let's take the new page and continue. What do you mean, Sarah? How do I find it? So this is the domain, right? And codomain. If I put here in my function as a sigma, 2 goes to 6, and 6, and 2 goes to 4 for tau function as a permutation function. So this is the spatial function. Permutation functions invertible. Invertible means one-to-one and onto. And also, I can think about the, reverse of sigma as a function, and reverse of tau is going to be exactly function. And next page, and continue what we have. What we have as a next. Okay. We have what? Okay, floor and ceiling function. So you know that one, I'm sure. Floor and ceiling functions. So it means there is the value. Okay, let's write the definition, then it's gonna be clear. There is the x be any real number, then x lies between two integers called, of course, called, there is bottom and, top value, we will say the floor and ceiling of x. It means if we represent like that symbol of x, this is the floor value, this is showing the bottom side of the x. It means the floor value called the floor of x denotes the greatest integer that does not exceed x. And if we represent x in that symbol, showing the top side of the x, it means the ceiling. So this is called the ceiling of x, right? And denotes the least integer that is not less than x. Okay, example, some example. Some example, okay, take that page off. Okay, if we have as a x 3.14 like the pi value, and there is the like y square root of 5, and there is the z is equal minus 8.5. There is the t, okay, let's say xyz, t as a 7, and u is equal minus 4, and that's it. Okay, u and s like minus 4.1. Okay, if we write to floor of x, this is going to be what? Also, you are using the coding, right? That kind of equalities. This is the function also. Yes, this is the tree. If I put like that as a ceiling of x is equal 4, right? And how about that like that? So less value as a floor value, you have to go smaller side as a minus 9, and if you write that like that, this is gonna be minus 8, and t, so this is the 7, again it is gonna be 7. If you write ceiling as a t, this is gonna be again 7, and if you write floor of minus 4, this is the again minus 4. Okay, right here as a u, I'm sorry. Okay, u, so this is the minus 4, and ceiling u is equal minus 4, and floor of s, so what is that one? Minus 5, and seal of s is equal minus 4. Okay, this is the example floor and ceiling function. And there is also absolute value function, or you can say, there is the coding side as an integer, or an absolute value function. Again, there is the x value, any real number. The integer value, we forgot y. I'm sorry. Okay, let's write the y is here as a, floor and ceiling. And as a floor value, this is the 2 point something, right? 2.2 or something. This is gonna be floor value as a 2, and y is gonna be ceiling 3. Okay, so integer and absolute value, this is also inside of the coding. The integer value of x written capital I and T x converts x into an integer by deleting or removing, truncating the fractional part of the number. So, for example, uh, it's not exactly floor or ceiling. So let's say there is the int as the integer 3.14, like the x value. This is going to be 3. Again, if we look at and y square root of 5, this is going to be 2. And again, there is the 8.5 is going to be minus 8. And this is a 7 and 7. And absolute value, so this is the 1 and second in that title. Absolute value of the real number x written ABS as a capital ABS x, or denote by in absolute value symbol like 2-line x, is defined as the greater of x or minus x. Hence, ABS 0 is equal 0, and for x not is equal 0, ABS absolute value of x is equal x, or absolute value of x is a minus x, depending on whether x is positive or negative. Actually, when you look at absolute value function, just you have to think about, there is the distance. If you go, minus side, for example, this is the minus, I mean, this is the numerical line, and here is the negative side, is a minus side, and this is the plus side. And absolute value is a distance. For example, here is the, let's say we have x. Okay, this is the x value, and here is the y value, and here is the, let's say, z and t. So if you write absolute value of x, I'm sorry, absolute value of x, or you can say absolute value of x, it means distance from 0 to x. And for example, x is equal what? Okay, x is equal, okay, that one, 3.14, 3.14, and t is equal, okay, 7. And y is equal, y was minus, okay, we have to find something as a minus, okay, minus y is equal minus 1.4, no, 2.7 minus 3.7. Okay, I have that values, left side of that line and right side of that line. When I write the x is equal 3.14, 3.14. If I write here as the absolute value of t, it is going to be 7. Absolute value of y, this is going to be distance. So 2.7, and absolute value of z is going to be as equal 3.7. This is the absolute value function. So we do not need to confuse our mind as a minus. Okay, dear friend. Okay, this is the page 2. Page 2 and page 3. Page 3. Remainder and modular. Function. And modular. Arithmetics. Is a new function. Okay, now different than x, there is the k. Let's k be any integer. And there is a capital M be a positive integer. Then we will write as a k in module, okay, is a MOD M. So this is the notation, and we will read that as a k module m will denote the integer remainder when, okay, this is the explanation, when k is divided by m. Okay, here is the end of the sentences. M, more exactly, k module m is the unique integer are such that there is the k is equal, this is the equalities, m times q plus r, you know, there is the r in the range of equal to 0 or less than to m. So example, you can write some example. Example. Okay, for example, 25 as a module 7. So what is gonna be is equal, that equalities, yeah, 4. How? We divide 25, right? So according to that equalities, Emre is writing, okay. Here actually, right, 25 is equal 7 times 3 plus 4. And then we will write 4 is here. So this is the remainder side of that equalities. An example, okay, 26 is a module 5. This is equal 1. And this is easy for you, I'm sure. And 35 in module 11. So of course this is gonna be 2. And so on. So, okay, there is the negative side. If, so this is maybe a little bit strange for you, is negative. Divide k by m to obtain a remainder is our hat. Then k module m is equal m minus our hat when our hat is not is equal to 0. Okay, let's write example for that condition. If there is the negative k, what we are gonna do? Okay, let's think about that one. We have minus 25 is a module 7. This is gonna be is equal minus 4, right? But according to that definition, I will add here as a 7. 7 minus 4 is equal 3. And again, minus 26 as a Module 7 is equal what? Minus 5. And we will add here as a 7 and is equal to. And there is, that kind of number, minus 3. So I will add here as a 8, then is equal 5, and so on. Okay, new one, what we have. Exponential function. So there's some, details of the remainder and module arithmetics. Best application area of the module function or that kind of remainder. You have to chance or ability to hide your information using the modular arithmetic. It is like the, what, cryptography. So this is also really good area to work on, coding. Exponential function is a new one. So that one also. We call the following definition. For integer exponent where m is positive integer, a to power m means is equal, there is the a times a times a and a. It means there is the m times a. So if a to power 0, this is gonna be is equal 1 for all number. If there is the a to power minus k, like we will say this is the 1 over a to power k. So this is the exponential function representation. And what else? Exponents are extended, include all rational numbers by defining for any rational number like m over n. So this is the a power m over n is equal square root of am as a squared degree n, or we can write as a n degree square root of a in parentheses to power m. An example like 2 to power 4 is equal, 2 times 2 times 2 times 2 is equal like 16. And if I am going to write as a 2 to power minus 4 is equal 1 over 2 times 2 times 2 times 2, this is equal 1 over 16. If I'm going to write 125 to power 2 or 3, so it means I'm going to take the power as a 2, and I'm going to take the power as a square power 3. So this is gonna be is equal what? This is the is equal 25 as a 5 to power 2 is equal 25. Okay, page 3, and let's do new page. Is a page 4, and there is also explanation as an exponential function. In fact, exponents are extended to include all real numbers by defining for example x any real number, a to power x is equal, there is the limit r approaching to x, r to power a to power r, where r is a rational number. And logarithmic function, our new function, so when I check the chapter titles, this is not enough to complete that chapter today, logarithmic functions. So logarithms are related to exponents as laws. Let's be a positive number. Logarithm of any positive number x to be the base b can be written logarithm b base x. So this is represents the exponent to which b must be raised to obtain x. So if there is a y is equal logarithm b base x, and this is also is equal, b to power y is equal x. I'm waiting the stream. So dear friend, can we do a break like 10 minutes? Then we will continue because I'm feeling tired. Okay, 10 minutes break. I will leave the page like that. Then I will continue. I will stop to record of the lecture. Okay. Then we will continue. And we write some example. If there is the base 2 logarithmic function as a 8, this is equal 3, right? And it means there's the 8 is equal 2 to power 3. If we have logarithmic function as a base 2, 64 is equal as a 6. So it means 2 to power 6 is equal as a 64, or 64 is equal to 2 to power 6. And logarithmic function as a base 10 and 100 is equal to, as you see, and 100 is equal 10 to power 2. And if there is a logarithmic function as a base 10, 0.001, this is going to be is equal minus 3. So how it is going to work? 0.001 is equal 10 to power minus 3. So this is also is equal 0.001 1 over 10 to power 3. And what else? As an example, there's the explanation as a furthermore, for any base b, we have b to power 0 is equal 1, and b to power 1 is equal b. So logarithmic function as a base b, 1 is equal 0, according to that. And also logarithmic function as a b base b is equal 1. This is the, some trick case for the logarithmic function. And there is also the logarithm of a negative number Okay, dear friend, can you see shared page, right? And there is no problem for video streaming and my voice. Can you follow the synchronously everything, speech and stream of the video or shared page? There is no problem. Okay, thank you. And let's write that one number and the logarithm of 0 are not defined. And there is also frequently logarithms are expressed using approximate values. For example, we can do approximation. For example, like logarithm 10 base to 300 is equal to 2.4771. And there is also, logarithm e base 40 is equal to 3.6889. There is some special application of the logarithm, but these are enough for us, and we don't need to do any details. We know how to calculate and how to write our function in logarithmic function. So let's write page 5 with the new title. This is the relationship. Okay, let's make it faster. Relationship between exponential function and logarithm function. Okay, let's write the basic relationship of the exponential and logarithmic function. F of x is equal to b to power x, and there is as a g of x as a logarithmic function base b to x. Let's draw the graph form of that two function x to y axis. Okay, f of x is going to perform like that. So this is the f of x as a 2 to power k or 1, 2 to power x function like that, and x is equal anyway, and there is the g of x gx is equal logarithm base 2 to x, and here is the x axis and y axis. So 1 is here and 1 is here. So these two function to reverse to each other, right? If I do like a line, like the function hx is equal x, this is the line function. You know, according to that line function, f of x and g of x like the symmetric to each other, but we can say these two functions inverse to each other, right? So we can say, okay, let's write here. Okay, we can say f of x and g of x are inverses of each other. So that's it for us to see a relationship of exponential and logarithmic function. A new one as a sequence, as a new title, sequences, and index classes of sets. So we will define that type as a spatial function, sequences and index classes of sets are spatial type of function. With their, of course, with their own notation. They have some spatial representation. So what are those as a sequence? Sequence is is a function from the set n as a natural number 1, 2, 3, and so on of positive integers into set A. The notation an is used to denote the image of integers n. And denoted by A1, A2, A3, and so on, or we can write A sub n is the number, is the member of n. So that kind of notation is also possible. That one is also possible. Or basically, or supply, we can write A sub n. This is also a representation of the sequence. If a sequence is, finite sequence, on A, we can write like A is equal, okay, A1. Let's say this is the A1. 1, 2, 3, 4, and M. So for that one, we can represent to that sequence also A1, A2, A3, and so on AM. Such as finite sequence is sometimes I'm sorry, I have to make it shift to up that page, called list of M tuple. Okay, this is the page 5. Okay, example, let's write some example, then jump that one. Okay, page 6. Example. One, 1/2, 1/3, 1/4. So we can define or represent that set an is equal 1/n. And let's say we have a series or sequence 1/2, 1/4, 1/8, and so on. So for that sequence, let's say B and we can define that sequence is a 2 to the power minus n. Okay, let's go. 5 page is here. And continue like that. Okay, you're welcome. And what else? So there is, some strange series, or I mean sequence, like this is also important. Sequence 1 minus 1, 1 minus 1, and so on. We can write that sequence as a n minus 1 to power n plus 1, or similarly or equivalently, we can write also en sequence minus 1 to power n. N is going to be 1, 2, 3, and then you will get that sequence or that series. Okay, there is the there is a strings. Let's write that one. Let's say there is the set A is finite and A is viewed as character set of alphabet. So this sequence called as a string or word. String or word is called a string or word. And this is enough for, I think, explain sequence and string. There is, we put the index classes, but inside of that title, there is this summation function. Okay, let's write the summation function. So this is also well known from you, I'm sure. Summation symbol and sum. This is the Riemann sum. This is also represent us to a kind of sequence like represent a sequence like A1, A2, A3, and so on. Let's write the representation of the summation. Let's say J1 to N, AJ is equal A1 summation. Let's add here as a summation. summation a1 plus a2 plus a3 plus and so on. There is the a sub n. If you want, there is going to be some kind of, you know, marked value like j is equal m to n. Here is the a, j is equal a m plus a m plus 1 plus a m plus 2 and so on. There is the a n. So example, let's say we have I is equal 1 to n. There is the ai bi. Then we will write ai times bi. Okay, let's say ai times bi. We will write first a1 b1 plus a2 b2 plus and so on. There's the a n bn, a sub n, b sub n. We can also write j is equal 2 to 5 in Riemann sum as a j square is equal first term of that sequence is a 2 to power 2 plus 3 to power 2 plus 4 to power 2 plus 5 to power 2 as a series form in Riemann sum and so on. And let's write the new title as an indexed classes of set. Let I be any non-empty set and let's say there is the S be a collection of sets and indexing function. Yeah, there is the indexing function from I to S is a function, of course, is a function f I to S, and for any I is element of capital I, we denote the image fi by a sub I. So this is the indexing function. This is the indexing function. I'm correcting my f, and then we can write a sub I is a member of capital I, or we can say a sub I is a member or element of I, and basically or simplify just AI. Okay. do we have to complete the indexed? Okay, there's the one more definition that we can write, maybe example. The set I is called the indexing set. And the elements of I are called indices if F is 1 to 1 and onto, we say that S is indexed by I. So that's it, I think. Let's write new function and new page. Recursively defined function. So this is the important for our department. Recursively defined functions. A function is said to be recursively defined if the function definition refers to itself so this is the important function is refers to itself in order for the definition not to be circular, function must have following two properties. What are those properties? First one, so you are looking for recursively function, so it must refers to itself. So these two part really important to that function, and there's two properties. First one, there must be a certain argument called base values, for which the function does not refer to itself, and second one, each time the function does refer itself, the argument argument of the function must be closer to a base value so these are the two properties of recursively defined function. So what are those as a recursively defined function? First, and easiest example is a factorial function. Factorial function. What is the factorial function? The product of positive integer from 1 to n inclusive is called n factorial and is usually denoted by n factorial. So this is equal, that function is equal, I'm sorry, so n factorial is equal n times n minus 1. You know, it is refers to itself again, n minus 2 times n minus 3 and so on. There is the 3, 2 and 1. So make a small dot between the dot numbers. 3, 2 and 1. Here is also multiplication as a dot. So also we will define as a 0 factorial is equal 1. 0 factorial is equal 1. And 1 factorial is 1. And 2 factorial is 2 times 1 is equal 2. 3 factorial is equal 3 times 2 times 1 is equal 6. And so on. Let's write the 4 factorial is equal 4 times 3 times 2 times 1 is equal 24. And 5 factorial is equal 5, 4, 3, 2, 1 is equal 122. And 6 factorial actually is equal 6 times 5 factorial. So this is equal 722. So this is the factorial function. This is also a recursive function. It is referring to something inside of the, itself. Okay, let's make it clear, then I will complete that lecture. So I'm thinking to do some extra lecture for, I think, that evening lecture hour. We have evening lecture hour, right? I'm gonna check my schedule. Yeah, there is, we have a chance to do some extra lecture at 7 as a evening. Nevdur Rahman, I didn't separate any time to check or grading your midterm, but I announced the solution from UBs. Also, I did the video record to solution, and I published that one from the YouTube. So I don't know, Kadir. I will check what is happening in your exam paper. Then I will evaluate them. Okay, example or explanation. Yeah, but one, there is the mailing problem from the server side, because I'm receiving your email like the 5 days later. Okay, when you send me email, I'm receiving your email like the 3 days later, 5 days later. So next time, if maybe final exam time, I'm gonna do some Zoom page, like the meeting page. If you have a question at the exam time, you will attend that Zoom class, then you will ask your question. And this is gonna be helpful for you, I think, because I was waiting on the computer your midterm time, and I wait your email. I check your submit of your answer, but I didn't get any response from you. Then also I add some minutes to your response. I mean your solution. Yeah, of course it's gonna be online. I mean, what we did in midterm exam, we will repeat for the final exam also. Anyway, okay, I will continue evening lecture time at 7 with the, recursively defined functions. And we were writing a factorial function. Then I hope I'm gonna finish that chapter. I hope if I finish that one, this is gonna be really a good gain for us. Actually, yeah, I want to get to, graph theory. Graph theory is really important for you. I mean, our department. So I don't know what is the percentage of the midterm. So what is the regular issue in university right now? It is the 40 or 60% midterm exam. I don't know. Okay, I will talk with the department. Then I will announce to you. So we have two things, midterm and final. Okay, see you, dear friend, to evening lecture at 7. I will prepare some, again, a title from that chapter. We will cover all. That's all. Thank you for coming my lecture. I'm really happy. You are like 40 students at the beginning of the lecture. Now 35. Okay, see you, Emren, Abdul Rahman. Okay, bye for all. Thank you, Kadir.